I forgot to record this whole time. What's a way of telling if two means are different? We've been doing it a lot this semester. How do we test to see if means are different? You've written 2 reports now on this particular method. Yeah, we can just run an ANOVA. In this case, what are we going to run an ANOVA on? We want to know if the covariate is different across the groups. So in this case, it would be what? Nope, not analysis 3, because analysis 3 is score as it's determined by group. We want to know what? Nope, because we want to know about the covariate. What's the covariate in this case? IQ. We want to know how IQ is influenced by group, right? And one of the things we find is that even though it appears from our plot earlier, it appears that the IQ of the drug group is slightly higher than the IQ of the placebo group. That difference in IQ between the two groups is not significantly different. So we meet that assumption of the analysis, and then the last assumption is the parallelism. And once again, we know how to do this. Once again, this is simply going to be what analysis 3 was, which is a linear model of score as it is determined by group, but it is also influenced by IQ. But in this case, instead of adding IQ to the model, we multiply IQ to the model so that we get the interaction term. And then this will be on the data frame that we've been working with this whole time. And then we can get the summary of that output and when we get that, what we see is that group is significant, IQ is significant. Now note, look what has happened here. This is the ANOVA table that you get when you just add the covariate in as a covariate in an analysis of covariance. You have group has an effect, IQ has an effect. The sums of squares of group is 73.98. The sums of squares of IQ is 52.12. Those two things haven't changed when you put the IQ in there as a possible interaction. What has happened is this 20.91, which is the residual variation, some of that variation has been split out into this group by IQ interaction. And because the amount of variation that is accounted for by that interaction is really tiny relative to the residual, it basically tells you that that interaction isn't explaining much variation. Because it only, of that 20.91 sums of squares that was in residual, it only explained 1.39 of the sums of squares, which then makes it non-significant because it's not a significant amount of the residual variation left over. Remember, residual variation is variation that we can't explain through any other means. Well, one of the means of explaining variation is by the interaction between the covariate and the two grouping variables that we have here. And in this case, it just happens to be non-significant, which is what we're looking for because we don't want that thing to interact, because that violates one of the assumptions of doing the analysis of covariance. Okay? So we have analyzed this simple data set. We've calculated the adjusted mean so that we can actually graph the results of the analysis of variance, the analysis of covariance correctly. We've tested the necessary underlying assumptions that have to be met in order to do an analysis of covariance. And we find that all of the assumptions in this case fit, which is nice for a change. And it also allows us to review this idea that you can test whether or not lines are parallel with one another. So you guys are going to get a data set. I'll post it today. Have to go and find it. In this data set, I've described it to you in the past. Basically, you have a bunch of data having to do with one's rank, assistant professor, one's rank, associate professor, and then lower down there are full professors. And then you also have the professors divided up into males and females. You see that in this particular time frame of William Jewell College, most full professors happen to be male. We have this many female full professors, and we have a lot more full professors who are male. That has to do with the fact that this was done back in the early 2000s. You also see that there are relatively few assistant professors relative to the full professors. Once again, that has to do with hiring practices back in the 60s and 70s and this demographic shift that William Jewell College has been going through in the last decade and a half. We have a much younger faculty now than we did when I first got here, simply because people have been retiring, and as people retire, we hire new people. And then what you have is the years of service. So your number of years that you've served here, if we get periodic raises that apply campus-wide, the longer you've been here, the more time you have to accrue those raises. And so years of service is one of the covariates. It's just one of the things that it is the covariate in this case. So in this case, you're going to be running an analysis of covariance, and the analysis of covariance will be looking at salary as it varies by rank. Are you an assistant, associate, or a full professor? And by sex. Do males get paid differently than females? But you have to take into consideration years of service, because you'll note here that there are two assistant professors who've been around for 26 and 34 years apiece. At William Jewell College, like at most places, if you don't have a PhD, you can't advance beyond the assistant professor level. This happened to be two individuals who had been here for a really long time, who had master's degrees, didn't have PhDs. So they had been here for 2 or 3 decades, but had not advanced past the assistant professor level because they didn't have the terminal degree in their field. And so you have to consider years of service. And what you'll see is that this person here who's been here for 34 years is making significantly more than all the other members of the assistant professor pool. And so you have to account for years of service in order to kind of make sure that you're scaling these data appropriately. Now, what you could do is you could divide salary by years of service. But once again, we've already talked about why calculating these kinds of ratios is usually a bad idea statistically. So what we'll do instead is we'll do an analysis of covariance. The question that the dean at the time had for me was, do the faculty salaries, are they different by rank? And not only are they different by rank, he asked me about salary compression, which basically means, are the salaries as you move from assistant to associate, is that gap similar to the gap that you see when you move from associate to full? What happens when you get to full professor is you don't have any more career advancement events. There's not a super full professor or a super duper full professor. You get here and you're an assistant professor, then you're an associate professor, then you're a full professor, and you've pretty much topped out. And so there aren't more promotions that allow you to get raises as you are here. And what happens is over time you have to offer assistant professors more and more money to get here each year because inflation and everything else. So the assistant professor salary tends to go up while the full professor salary tends to stay relatively the same. So you might be getting this thing that they call in the business called salary compression. So the dean had two questions. Is there salary compression at the full professor level? And the other question that he had was, are males being compensated differently than females? So once you correct for something like years of service, it happens to be these two guys who have been here for forever. They happen to be two guys. They're both male. So the question is, do males get compensated differently than females? Does that differ across ranks? So is there an interaction, for example, between rank and sex in the salaries that we're paying faculty, given differences in the number of years of service, which we're going to factor out as a covariant? So those are the two questions that are being asked. Is there salary compression at the full professor level, and are we paying males and females differently? And we have to account for years of service when we ask those two questions. So that is the data set. I'll post a made-up letter from the dean recruiting you, a faculty member, to do this analysis. And these are the data that you have to work with. So this requires that you do a two-way analysis of covariance, and we have only done a one-way analysis of covariance in class. So what I want to do is take you through a two-way analysis of covariance, and I want to use the body condition data, because I asked you to analyze the body condition data with a regression, but you could have just as easily done it with an analysis of covariance, and ultimately, to test for parallelism of the lines, you have to do an analysis of covariance anyway. So go find your body condition data and read that in, and then filter it so that it only has Hemidactylus tursicus in it. So you'll see that in this data set, there's Galveston data where there's another species of lizard that lives in Galveston, so you need to filter that out so that you only have Hemidactylus tursicus. And so here's my data file, and you can see that there's nothing but HTs in it all the way down. So run these lines of code and put, oh, you don't have a sticky because I didn't put them out today. Do you need stickies? No, okay. Look bored. Have bored looks on your face when you're done with the task. Yeah. Well, what happened there? That's weird. What did you hit just now?
I thought I hit option return that money.
Well, you need to hit command return. You hit option return all that.
Yeah.
Okay, go down here. Escape. Where's your escape button? How do you escape? No, not. Don't close it. Oh, okay. Well, no. Still not doing it. Why does it? Why do you touch it and it does things and I touch it and it does nothing?
I don't know if there's a.
What did Apple do with the escape key?
Okay, that's fine.
Okay. Did you load all your? Did you load all these earlier?
Mm-hmm.
Oh, slider, filter. All right, did everybody get this done? Okay, so the next thing is just specifying the model. So in this case, we're going to have weight, and weight is determined by population and collection and snout vent length, but there's an interaction modifier between population and collection, and there's a plus modifier between those two things and snout vent length for the data frame. And hopefully that will run without error. And you will then run summary AOV, and that should give you an analysis of variance table. Did everybody get that to run? Haley? Okay. So basically it's telling you that there's a difference in the populations. So the populations are different sizes. There's a difference in the collection time. The sizes of the geckos differ by collection period, winter versus summer. There is a significant correlation between snout vent length and weight. Duh, we already kind of knew that was going to be the case. And then when we look for this population by collection interaction, we find that that's not significant. So population and collection they're not affected. Population, the weight of geckos in Galveston versus Oklahoma is not differently affected depending on whether you're talking about winter or summer. It's just that one population is just generally heavier than the other population, and one time period is generally heavier than the other time period. And the reason that we can detect those main effects is because we've removed all of this variation that is due to the length of the organisms. So this is a somewhat different answer that you get when you're just looking at this with regression. But at the time that I asked you to look at these data, you didn't have analysis of covariance in your toolbox. So this also illustrates to you that there are better ways of analyzing data as you know more ways of analyzing data. And so we would get a different answer if we were analyzing this with analysis of covariance. As it turns out, analysis of covariance is the most appropriate way of analyzing these type of data. For the faculty salary data, one of these main effects would be rank. One of these main effects would be gender. The covariate is years of service. You will have a rank by gender interaction term, and then you'll have a residual term. So this is analogous to what the faculty salary data will be. Questions?
Like the same test on how to make what we've been doing? Or like, is there anything
What same kind of tests? Oh, for
normality?
oh yeah, same thing. You can get the residuals from this model. So residuals from BC model. Whoa, I didn't ask for it correctly. And so there are 153 geckos in this analysis, and so there are 153 residuals. If you sum those residuals, let me do this. Once again, that should be practically 0, and then you can run a Shapiro-Wilk test on this. Yeah, so all the same things. Once again, when you run homogeneity of variances, you're going to get a, it's going to groan because you've included the covariate in there. Just remove the covariate from the analysis. So yeah, you can do all the same things. You can also change this model to be a test of the parallelism. So I'll just copy this model and change this from a plus to an asterisk, and that will give me when I ask it to give me the output in the correct way, it will give me an ANOVA table that now has population, collection, snout vent length, population by collection interaction, population by snout vent length interaction, collection by snout vent length. But it's this interaction down here that we are interested in. How does snout vent length interact with both collection and population? And that is not a significant interaction. So all the things that we did with a one-way ANOVA, we can do with a two-way ANOVA. Same coding and everything else. You're just including that second factor. So one of the nice things about things like ANOVA is it doesn't matter whether you have one factor or two factors or three factors or five factors that you're testing. The fact of the matter is all you do is just add those to the model. The ANOVA table gets more complicated the more of them you have, but it's all the same math and it's all the same interpretation ultimately. Okay? Now, one last thing that I haven't shown you. So in this case, we had a significant ANOVA. What's one of the things that you would want to do right after a significant ANOVA? Okay, you will want to visualize it, but we've already talked about how we do that in other ways. What's a more statistical thing that we would want to do other than just visualizing? We want to do something like post-hoc comparisons. So we found these differences. We want to know what those differences are and what the nature of them are, right? So there's a population difference. Well, what is that population difference? Are Galveston geckos bigger than Oklahoma City geckos, or Oklahoma City geckos bigger than Galveston geckos? How would we normally do that? We would normally do a Tukey's test. So how do we do a Tukey's test? We would do Tukey's HD, and we could just do that in theory on the model. So in this case, the model is, in my world, BC model. I don't know what you called your model, but let's try that. Oh, no! We cannot apply Tukey on a significant difference test to a linear model. As it turns out, the person who wrote the Tukey's test that we've been using actually wrote it to only interact with AOV as a function. What else have we used to run Tukey in the past? We've used Agricola, right, to run a Tukey's test in the past? Am I recalling that correctly? And what is What is the code for that? So I'm just adapting. This is analysis. This is actually BC model. BC model. And in this case, the treatments are pop and collection. So I've just gone over to the rat-fat script that we were using earlier, and I'm going to now just copy that into my Ancova Live script. And this, in theory, if Agricola will do it, should give us a two-keys test and an honest significant difference test on BC model, which is the model that we are working with, looking at differences in population and collection. So if we run that, what does it do? Oh yeah, it did it. It looks like it did it. And let's see if it is doing it. Son of a bitch. It looked like it did it. So we can see that Oklahoma City in the summer. Oh, it did it, but it did not do it correctly. Oh no, I'm thinking of temperature. Sorry, I was in temperature head. It may have done it correctly. So Oklahoma City in summer and winter are not different, but Oklahoma City in summer and winter is different from Galveston in summer, and Galveston summer is different from Galveston winter. Now, what it doesn't tell us is what those actual weights are, except that here are the actual weights. And it looks like Oklahoma City in the summer and winter are generally bigger than Galveston in the summer, which is bigger than Galveston in the winter. So you can run a two-keys test after a two-way analysis of covariance, just like you can run it after a one-way analysis of variance or a two-way analysis of variance. It's just that you can't use the 2-key HSD code. You have to use the Agricola code in order to do it. So that is that right there. So once again, everything you can do with a one-way analysis of variance, you can do with a two-way analysis of variance. Everything you can do with a one-way analysis of covariance, you can do with a two-way analysis of covariance. You just have to maybe use a different package in order to do it. So you can do all of your multiple comparisons just like you've done them in the past. And yeah, that's it. You have hopefully learned a ton of statistics this semester. Any questions? Yeah.
So we come in on the day of the final.
You will not come in on the day of the final. You will submit a report on the faculty salary data on the day of the final. And that's it.
So let's do it next Friday.
Next Friday, yep. I'll post the faculty salary data and the instructions today, and I'll have a due date next Friday on it. Yep. Questions? Do you feel like you've gotten any better at interacting with R? Your R anxiety has gone down, hopefully, over time? Okay, good. All right. You've been sent emails asking you to fill out course evaluations. What I'm about to say applies to this class as well as every other class that you take at William Jewell College. Fill them out. Fill them out honestly. The promotion and tenure committee looks at both your numerical responses and your comments when they decide whether or not people get promotion and tenure. I'm a full professor, so I don't have any other steps to go through, but every 5 years my teaching is evaluated in what they call periodic review. And if you say terrible things about me as a human being, they will take those into account. If you say great things about me as a human being, they will take those things into account. Strangely enough, they take those into account in the same way that they take into account your comments about me as a teacher. So if you felt that you got good teaching in this class, comment in ways and respond in ways that indicate that. If you felt like you got shitty teaching, then you need to ream me out and they will eventually get rid of me so that you don't inflict me on any other group of students. So answer those honestly. Know that your professors read them. Know that the promotion and tenure committee reads them, and they do have weight, in my opinion, an inordinately large amount of weight in promotion and tenure committee hearings. So for this class, for every other class that you have, fill them out honestly about the person's performance in the course. When I was department chair, we lost a faculty member in biology because she got negative teaching evaluations. So it does have consequence. So take them with the same degree of seriousness that other people on campus take them. With that said, if you have any questions as you prepare either the linear regression report that's due later on today or the faculty salaries report that is due next week, talk to Hayden. He knows from experience my door is open a lot. I mean, it's closed, but it's open. Like I said, if you need help with coding, just let me know and I will do my best to help you out. Sorry, Hayden, you're just the person who has been to see me the most this semester.
Would it be
Yeah.
easier for the report to do like two separate written reports for two?
Oh yeah, so I was talking about Hayden about this just the other day. Since it's two very different analyses, the way I would probably write this if I was writing it is I would write a methods for the temperature data, followed by a results for the temperature data, followed by a methods for the body condition data, followed by a results for the body condition data. Another thing that I meant to mention this and it fell out of my head. For the temperature data, what you're basically doing is testing a bunch of regression models to see if the slopes are different from zero. So you could talk about those in a really long, rambly paragraph that kind of goes through each of those models individually. But maybe a more efficient way of doing that would be to make a table where you have like population and season. And so you would have Galveston summer, Galveston winter, Oklahoma City, summer, Oklahoma City, winter. And then for each of these things, there are certain things about the regression that somebody would want to know. For example, they might want to know what the degrees of freedom are, which tells you something about the data, how big the data is. So for Galveston summer, it might be 1 degree of freedom for the regression and 50 degrees of freedom for the residual. But then you want to know what the intercept is. You want to know what the slope is. You want to know what the F statistic is associated with doing the test on that slope. And then you might want to know what P is. Because you've given them this, they know that body temperature is equal to whatever the intercept is plus the slope times wall temperature. So from this table, they can extract the equation itself. From this table, they know what the sample size is of the different combinations of population and season. They also know what the results of your statistical test of that slope is. This might be a more efficient way of doing it than writing this all out in a paragraph. In the paragraph describing the results, you can say, all of these correlations were significant. Table 1 to see the specifics of each of those. And so that might be a way to quickly and easily organize information for your reader.
Okay. Gotcha.
It's the kind of thing I would do if I was making a report.
Gotcha. Thank you.
And it saves you some writing.
Yeah.